So in this set of Snap Circuits videos, we're continuing to look at the PC set of projects with the CI-73 system, starting with project PC4 here and ending up with PC11. Now I will say I noticed in the last video, and I'm sure everyone else has noticed too, that, and again I don't know why it happened, but the first three projects, the intros on them, somehow the video froze up right at the start of those during the video rendering. I don't know exactly why it did that, but I didn't want to completely redo the video rendering and then re-upload it and all that stuff, so I kind of just left it as is. But for the most part, I think everybody still sees how the video turns out even afterwards. So anyway, we've got project PC4 here, which is the Light Sounds PC. That's how it looks in the book, and there it is on our board. So let me go ahead and get Cam Studio recording the oscilloscope here. And let's turn on our circuit. Of course, it helps if I start the oscilloscope first too. So let me get this into our half millisecond division. Try to get a trigger on there, and let me bring this scale down a ways. So our waveform is kind of bouncing around there a little bit, as you see. But when you look at these things here, of course, you can tell from the sound coming out of the alarm IC that the waveform is constantly changing because it's making a sound basically like a siren right now. Or an alarm, whatever. Anyway, as you see, again, the frequency is changing up and down with the waveform because, again, it's producing audio from our alarm IC based on its current setup here. And if we look at our FFT setup, again, you can see the change on our frequency over time there as the signal here bounces up and down, and of course it also goes in and out here as well. So let me get out of the FFT mode. And now we're going to move on to project PC5. So on that we're going to connect points X and Y. So we're going to add a 3 snap here, and that's going to give us the machine gun sound effect. And of course you see that our 2.5 volt lamp is going on and off there. And if we look at our waveform now, you can see, of course, the oscilloscope cuts off a couple times as the output from there turns off. But we're getting a little bit of a different waveform output again as it oscillates to produce the audio there. And again, we'll check this out on the FFT mode. I'll put this on the right scale. And you see with FFT it stays pretty stable. It's just that you see when the circuit loses power there, every time it cycles on and off, we see the oscilloscope cut out there as well. Back to that mode. So now, with project PC6, we're going to remove the connection between X and Y here, and I'm going to make it between T and U in the book, which is going to put it over here. So now we get more of a fire engine sound effect. And here, because of the way that the fire engine sound effect works on there, you can clearly see it on the oscilloscope, as when the frequency gets higher, the waves come closer and closer together, and then they kind of spread out and come together. Spread out. So it's very clear on the oscilloscope here how the fire engine sound effect goes up and down in frequency. And we'll again, we'll look at this on our FFT mode. And FFT mode also shows it pretty clearly as it oscillates up and down in frequency. Because as you see, these peaks come closer together and then spread out. So as the frequency gets higher, these peaks spread out. As it gets lower, they come closer together. So let's move on to project PC7. So we're going to take this connection away, and now we're going to add a connection between U and Z, which is this right here. And now we get an ambulance sound effect. And again, looking at our waveform here, again, depending on when the oscilloscope reads the information from the snap circuit here, you can see when it's at a lower frequency and when it's at a higher frequency, as the circuit is kind of oscillating back and forth like that. And the way FFT shows, again, you can see the difference in the FFT as well when it's at a high frequency versus low frequency as it's alternating back and forth. The higher frequency, the peaks spread out. At the lower end of the frequency, they come closer together. Again, because of the way that the Windscope software is polling every third of a second or so, again, it sometimes can't keep up with the circuit oscillation there. And again, we're comparing the waveforms between each project. So now we're going to look at PC8. So for that, we're going to remove this connection, and we're simply going to move this over here. And bring this back here. So now apparently it sounds like a water faucet according to the book, and you see that our lamp is very different from all the previous versions of the project, including our waveform here. Our waveform looks very different from all the previous projects. Of course, the sound is also very different. But again, you can still hear that the frequency of the sound goes up and down. But because of the way that the alarm IC is functioning, our waveform looks radically different. If we look at our FFT also looks quite a bit different. But you can still see the effect just as the frequency goes up, that you see these points spread out and then come closer together as it goes lower. So now we're going to look at project PC9. For that, we go back to where we were before, but this time we take out the 2.5 volt lamp and the whistle chip and replace it with our speaker, and then we will hook our connections up to that. So move our alligator clip here. And because it's nighttime, I'm kind of going to cover this up because I don't want it making too much noise. Yeah, that's a bit loud for nighttime here. Let me bring the scale back. Oops, I think one of my clips just changed now. Yeah. So I think what I'm going to do here is use wait mode. And so with wait mode there, we can try something a little different. You can see our waveform here, and when we compare it to something like project PC4 where we started, the speaker draws more current than our whistle chip did. So when we actually compare this, our waveform is actually going to appear larger than it did in PC4. Again, because our speaker pulls more current, we actually have a larger waveform reading. we see this on the FFT scale, we can see it also looks a little different there as well. Again, I'm not running the circuit right now because, again, I don't want too much noise, but again, we're just demonstrating that the higher current use of the speaker there shows a much larger waveform in comparison to what PC4 has with the whistle chip and 2.5 volt lamp. So that is project PC9. So now we're going to move on to project PC10, which is going to be modulation. Oh, let me stop the video here. So here we are looking at project PC10, which is modulation. Here it is in the book there, and there it is on the board. So we're still using our alarm IC, but we have our microphone on the output there that we're monitoring through our Windscope software, and then our whistle chip can be introduced into the circuit through our press switch while everything is being limited with our R4 resistor. So let me get Windscope going here. Start it up, and then turn on power to the circuit. And you see when you look at our waveform here, you see that it's got peaks. Now I do have to mention here, you see my hand, I'm going to put it on the laptop and then take it away. And you see how that waveform is changing? This is one of the things, again, you have to keep in mind. And I put my left hand on the laptop and it's doing the same thing. That you have to be aware that you can influence interference on the circuit. So by putting my hand on the laptop, I'm essentially causing some interference there on the sound card part, and it's making the waveform actually come out smaller. And of course, if I touch the circuit, I make it actually higher. So this is just one of the things you have to keep in mind. But anyway, looking at project PC10 here with modulation, we see we have kind of a constant signal there, and it is actually fluctuating a little bit as I talk, because again, and this is going to come up here pretty soon, is that the microphone is picking up audio there, and it's being superimposed onto the waveform there. So, show here, I have a little straw, and I'm going to blow onto the microphone, and we'll watch how that waveform changes. Yeah, it might be a little subtle there, so let me make this a little bit smaller if I can. So what you probably saw there is the peaks of the waveform, and the waveform itself was changing as I was blowing into the microphone there, and I can do a little bit by tapping on it as well. And what we're doing there is we're demonstrating a form of modulation called amplitude modulation. So what we have is a controlling signal, which is the audio from our alarm IC coming out, which is what's being constant there. But then we're introducing another signal by our audio going into the microphone there, and then that gets superimposed on top of our current waveform here. And so this is how AM radio stations work when you're listening to AM radio. They have a controlling signal, which is the frequency of the station you're listening to, say 1000 AM, which is 1000 kilohertz. And then they have all their audio, like their voice or music or whatever they're doing on the radio station, superimposed on top of that signal, and then it's sent out over the airwaves, and then you receive it on your radio. So that's how it's demonstrating AM, or amplitude modulation. Now, there's another form of modulation here. I'm going to change it to this, or a half millisecond division scale. And of course, we've already been seeing this in the previous projects already, but if you note the waveform itself, the spacing between the peaks there is going smaller and larger, again, as the signal from our alarm IC is going up and down in frequency. And this is another form of modulation, which is frequency modulation. So with amplitude modulation, we're modulating the amplitude, or the height of the peaks on the waveform. Frequency modulation, we're changing the distance between the peaks of the waveform. So amplitude is the height, and frequency, of course, is the distance between those peaks. And again, you have FM radio in cars too. It's just a different form of modulation, and that's measured in megahertz as opposed to kilohertz that you have with the AM radio. So that's PC10. Now PC11 is filtering, and it's part of the reason why we have the whistle chip on here. So right now you see that we have our signal going there, but you see that it's a little jagged and it's got slopes and stuff as it's charging. But when we hold down our press switch and introduce our whistle chip into the circuit, of course we can hear the alarm IC going a little bit, but if you look at our waveform now, the corners of the waveform are now nice and round. So we don't have kind of a noisy signal there anymore. We actually have a nice signal that's nice and round. And of course this is what you have in, you know, car stereos and stuff like that, especially with people that like to really bump up their car stereos. They'll usually have some kind of large capacitor in the power circuit to filter out any noise from the car's electrical system, so you get a nice clean signal like this. Now, of course, the whistle chip is an example of a small capacitor. What we're going to do here is put an actual capacitor in, which is our C1, which is our 0.02 microfarad capacitor. Just this run right here. And this provides some true capacitance to the circuit. So when we put that in there, we won't hear anything, but if I hold our switch there, you can see we still got that nice rounding on our waveform there, so it's acting as a noise filter. So we still have frequency modulation going on, but now the signal is being filtered by our capacitor there to take out all the sharp corners and make it a more of a clean signal. So that's without it, and that's with it. So that's how Project PC11 works, and that concludes this set of Snap Circuits videos.